The first question that popped to your mind whenever we suggest a solution approach is why? In particular, whose pain point are we trying to solve? It turns out that many operating system subsystems need persistence. For example, file system. It has metadata such as inodes that say where and how files are actually stored on the disk. And this data structure, which is the inode data structure, is a persistent data structure. And while the operating system may manipulate that data structure by bringing it into main memory for performance reasons, finally, it has to put it back on the disk in a persistent state once permanent changes have been made to that data structure. And that's the reason why persistence is very, very important for building several such subsystems. So file system I gave you as an example. Similarly, runtime systems of many languages may require support for persistent objects that need to be stored on permanent storage. And all of these subsystems, what they would do is, in order to make it efficient from the point of view of processing, they will have in memory a cache copy of the persistent data that lives on permanent storage such as the disk. But if and when changes are made to those data structures that are in memory, they have to be committed back to the permanent storage so that there is consistency for actions that are being taken by these subsystems. So how can we provide persistent support for these subsystems? Well, one possibility is to make virtual memory persistent. Because if you make the virtual memory persistent, then all the data structures that are contained in the virtual memory become automatically persistent. Now, the upshot of doing that would be that the subsystems do not have to worry about flushing the persistent data structures from memory into the disk, because some other layer in the software stack is going to take care of it if, in fact, we make virtual memory persistent. That also means that if the system were to crash either due to power failure or due to problems in the software, meaning software bugs, recovering from such crashes becomes easy because the data structures are persistent, and anything that was done in the virtual memory of the process that represents that subsystem is going to be available in the persistent storage. The question is then, who will use it? Well, we're expecting that the subsystem designers will use such an abstraction if we provide it. But subsystem designers also care about performance, and therefore subsystem designers will use it only if the abstraction is a performant abstraction. In other words, it is not enough to come up with an abstraction, but it is also important to make the abstraction efficient. So if an abstraction is cheap to use, easy to understand, and flexible, then subsystem designers will use it. If it is not, they won't. So the question is, if we want to make virtual memory persistent, can we also make it an efficient implementation of the abstraction of a persistent virtual memory? Now, how can we make it efficient? Now, if you think about it, the virtual address space of a process, and let's say that this virtual address space represents the process that belongs to a particular subsystem, it may have persistent data structures that are strewn all over this address space. And if these data structures, persistent data structures, are written into, and if these persistent data structures are manipulated by the subsystem, and if we want them to be committed to the storage, then it requires that every time you touch a persistent data structure in-memory version of it and modify it, the on-disk version of that same data structure need to be updated. Now, what that means is, if these data structures are spread out all over the virtual address space, that could result in many I/O operations, first of all. Second, it could also mean that we may be writing to different portions of the disk. And both of these are bad news, because disk, by its very nature, it's electromechanical in nature, and disk is electromechanical in nature, and as a result, there are latencies associated with the disk, namely seek latency and rotational latency. And if the writing that we are doing to virtual memory, which is backed up by the persistent disk, is all over the disk, then it's going to result in many random writes to the storage system. and random writes are going to be resulting in very poor performance. So instead of doing this, what we would like to do is have what we will call a log segment. And the idea is very similar to the log structured file system that we have seen earlier when we discussed XFS. The idea is that when you're making changes to the virtual memory and you know what portions of it are persistent, every time you write to a persistent data structure that is in memory, then you write a log record that corresponds to that change that you made to that persistent data structure. So this is the change that you made to this persistent data structure, and this is the change that you made to this persistent data structure. The log segment is itself a data structure in support of these subsystems. So in implementing the persistent virtual memory, we have this log segment as a data structure that the implementation uses to record changes to persistent portions of the virtual address space. And because we are putting it into this data structure called log segment, we can write this contiguously. And of course, we have to commit these changes to the disk. But now you can see the difference in the picture between here and here. Here, we were doing random writes all over the disk. But here, we are writing the changes to the persistent data structures to contiguous portions of a log segment. And we can take this and store this contiguously on the disk. And that's the attraction. So these log segments are going to be stored contiguously on the disk, and therefore, even though we are making random writes in the address space of the subsystem that we are building that requires certain persistent data structures, because those changes are being recorded as logs in a log segment, and we are committing the log segment to the disk, we can convert these random writes to sequential writes and write sequentially on the disk. So two things we are accomplishing by doing that. The first is we are not making individual I/O operations where every time we touch different portions of the virtual address space, because we are writing it into this log segment, which may be an in-memory data structure. And therefore, we are reducing the number of I/O operations that we need in order to commit these changes finally to the storage. And second, because we are writing this contiguously, we don't have the random writes that we talked about. All of these will help make the design and implementation of a persistent virtual memory much more efficient. That is the key idea, which is there in the paper that I've assigned to you for reading, which is the LRVM paper.